Hi, this is video 2. If you haven't seen video 1, please do that. So I'll start talking about the topic in more details. Now, it will be usual for me to talk about the topic um, using a particular way that I find very useful when I think about mathematics. And there is an acronym I use for it. It's called HATLOGS, where H stands for history, A is application, T is the types of linear algebra that might be involved, L stands for the language, notations and that sort of stuff, O is operations, G is the geometric intuitions, and S is essentially the structures that we'll be talking about. So this is how this particular video will unfold. And so let's start with the main question about linear algebra, which is, first of all, what is a mathematical model? Now, sometimes it is also referred to more technically as a function approximator. But let's try to understand what this is. So, for example, if I have an XY plot, a scatter plot of some points, and these X and Y can be anything in particular. Let's say we're talking about the systolic blood pressure and the diastolic blood pressure. Just a toy example. And we obtained these points through what is known in science as a empirical observation. That is, we did some experiments, and for some particular disease or pathology, we found that for n number of patients, this is patient 1, this is patient 2, etc. We have a whole bunch of points. Now, in science, we can do an experiment, but this relationship between the systolic blood pressure and the diastolic blood pressure, that is when the heart is compressing and expanding or relaxing, it is not clear, at least mathematically, what this is. Is this part of a parabola? Is this some kind of logarithmic curve? What is it? Now, a mathematical model is essentially when or a model for that matter, is when we try to reduce the ambiguity that we have in language when we talk about something, and try to pin down the essential feature of something and express it as, let's say, an equation. So let's say this equation could be a parabolic equation, or it could be a linear equation. It could be a lot of things. But what we have found in science is that a lot of um, empirical observations and reality in general can be expressed in terms of straight lines. This is actually an equation of a straight line. So straight lines are simpler than a curved line, because if you have 2 points, there is only one straight line going through it. If we are talking about a curve, there could be so many types of curves that go through it. It's almost impossible to figure out, between 2 points, the complexity of that. But a straight line is a very simple thing. Between 2 points, you have a straight line. Now, what a mathematical model does is essentially gives us something portable. So if you say, okay, this bunch of points is actually a line, let me give it a different color, is a line, then I have a simpler way to talk about it. And this whole experimental empirical observation that I cannot carry with me, but now with a mathematical model, which is just an equation, for example, I can simply say, well, this relationship between the diastolic blood pressure is equal to, let's say, 5 times the systolic blood pressure plus 0.5 or something like that. Now this becomes something that I can carry with me, and I can foretell the future. I can predict something that I have not done an experiment on. So for a particular value of X or systolic blood pressure, I can actually come up with the value of the diastolic blood pressure without actually conducting any experiments, without any empirical observation. So that is where a mathematical model is helpful. And a linear model, which I'll talk about now, is one of the simpler models that not only fits when the underlying function is close to being linear, but even if it is curved, we can approximate a curve with a number of lines. So even when we don't have a straight line, that is, we have a curve, that can be broken down into a number of linear equations that approximate that curve. Now, what is a linear equation? And a linear equation is essentially when you have both y, for example, in this case, you have y and x. They are both to the power 1. That is a linear equation. Now you must be careful, because something like this, where you have a modulus of x, this is not a linear equation, although the power of x here is 1, because if you look at the curve here, for both the negative values of x as well as for the positive values of x, the values of y are always positive. So this is a case of a bifurcation. So non-linearity is essentially not always just curves. This is also an example of non-linearity, where things can bifurcate. Of course, when we talk about trigonometric functions, they oscillate like sine and cosine, etc., and they can explode like exponential or anything that is to the power of something. Those are all examples of non-linearity, but what is linear is essentially this. This is an example of something that is linear, and now I will go into the definition of what is linear in more details. Alright, so we are talking about linearity, and when we talk about linearity, we have to remember that linearity of linear systems are some things mathematically that are computationally civilized, because we're talking about straight lines. They behave well, and their solutions are predictable, whereas nonlinear systems like the ones that we talked about, which bifurcate, oscillate, or explode, are not computationally civilized. But we can domesticate something that is nonlinear by carving them out into smaller linear pieces. For example, the circle can become a polygon. So instead of a circle, we can essentially, these are all straight lines. A circle can become a polygon. A curve, for example, can become a tangent at a point. A curved surface can become a tangent plane. For example, when we talk about the Earth, and we talk about, let's say, this room, for example, this room is flat to me, right? So this room is actually an example of a tangential plane at a certain point on the surface of the Earth, which happens to be in Calcutta, right? So the reason of doing all this is that we convert all this chaos of nonlinearity. So the chaos of nonlinearity, we convert it into matrix algebra or linear algebra, and we'll talk more about matrices in a moment. But my point is that with enough small flat truths, we can stitch together, or we can simulate the curvature of reality and sometimes intelligence, which is what artificial intelligence is, of neural networks, for example. And even training a neural network is essentially relying on local linear approximations, which we will see in much later, at a later point, because something that is globally nonlinear, for example, if we have the function approximator of x-rays and the result, this is the input, the result is whether or not someone has cancer, say. So this is globally nonlinear, but when we train it, we use linear methods to arrive at this function approximation, which answers this question. And the entire field of artificial intelligence right now, which depends on machine learning, deep neural networks, is this function approximation concept, this mathematical model underlying it, which is a linear model. It's all linear algebra essentially, and probability and some calculus, where we are essentially reducing what our human brain is doing. For example, a pathologist looks at an x-ray and can tell whether or not someone has cancer, into a function. Of course, we cannot express this function as easily as one straight line equation, because it is not one straight line equation. It is a whole bunch of straight line equations that are stitched together. So the global nonlinearity is expressed as a whole bunch of stitched linearity, and that's how we can get to this function approximation. Ultimately, the whole idea is that we are going to create function approximation which are domain independent. That is, an AI should be able to do just about anything, which is a function approximation that is not dependent on a domain. That is, it's not just a doctor. It can be also a geologist, or it can be a mathematician, or it can be a musician. It can be whoever we want, because that function approximation is domain agnostic. Now, linearity requires a particular type of mathematics, which is f expressed simply as fax1 plus bx2, say, is equal to a f x1 plus b f x2. So what does this mean? Reality is not always linear, but sometimes it is. For example, if x1 is the cost of an apple, so if this is the cost of an apple, and this is the cost of an orange, then the function of the total cost, which is the total cost of buying a number of apples at a price of x1 plus b number of oranges at a cost of x2 is the same. So if we add this up, and if we do this separately, that is, if we buy oranges, if we add these two separately, that is a number of apples times fx1, which is the cost, again, the cost of just an apple, plus b number of oranges fx2. So this reduces to this reduces to this, and so essentially these two are same. So this equality holds. This is an example, right? So, but is this always true? No, it's not. For example, if f ax1 plus bx2 can be, in some cases, less than f afx1 plus b fx2. What is an example? Let's say f is the cost of an airline ticket. So if x1 is the cost of the departure ticket, so if this is the departure ticket, and if this is the, let's say, cost of the, so this is the cost of the return ticket, if we buy those two together, then this cost is usually, and I've seen it most of the time when I bought tickets from the US for India, I bought traveling from San Antonio to Calcutta and then from Calcutta back to San Antonio at the same time, and so that cost is much less than if I had bought a departure ticket that is from San Antonio to Calcutta, and then I had at a later point in time or separately from a different travel agent or whatever bought another ticket from Calcutta back to San Antonio. So always, at least in case of airline ticket, this relationship is nonlinear. So reality is not always linear. It is nonlinear, right? Now, when we talk about linearity, there is a very important fundamental point when we look at geometrically. It involves the origin. So for example, if we are talking about a function which is let's say a linear function which is in xy, and it is 2x and 3y, say. Now this is linear because if you put 0 0 here, the function, so t 0 0 gives you 0 0, but if you have t xy equals to, let's say, 2x plus 5 3y, then t 0 0 is shifted. So because this is now equal to 5 0, so as if the whole graph shifted. Now this is not allowed in linear algebra. That's why when I say that what kind of language or type, or in that mnemonic that I used first, the type of linear algebra, this type of linear algebra is what we are talking about in this course, and this is what we use in machine learning, etc. But it's important to understand that it's mixed with this other kind of linear algebra. This is called the affine linear algebra, whereas this can be just one matrix multiplication. This requires a matrix multiplication and shift. In our examples of straight lines, where we have seen that y is equal to mx plus c, this is actually affine. If y was equal to mx only, this was linear. But as soon as you have a c value, which is, in case of a line, this is essentially the c value. So it's shifted. So this is an example of affine, and this is linear. So this is vanilla linear, which is the most important thing, and this is the affine. And as I'll now give you a concrete example, we will go into looking at what we had looked before when we were kids in school. We looked at simultaneous equations. We looked at linear simultaneous equations. So I'll go to that example now and show you how that is connected. That is how straight line equations that like this are actually connected to linear algebra. So now let's talk about what a vector is. A vector is a displacement, in n dimensions. That n can be 0, it can be 1, it can be 2, it can be 3, it can be a general case of n. Now we are going to take this example that we will soon talk about, where we will talk about two different camera angles called the row picture and the column picture. But this is what we have seen in our school days in simultaneous equations, the x and y. Now a vector I will always represent like this, which is a column vector form. So in our case of 2 dimension, when n is equal to 2, we are talking about a plane like this, the surface of this tablet that I'm writing on, or it could be a blackboard, or it could be any a sheet of paper that is lying flat. And when n equals 3, we are talking about the space that we occupy. Now, we are three-dimensional creatures. We are trapped in three-dimensional space. We can only we cannot escape the three-dimensional space. We can only look within two-dimensional and one-dimensional. When we talk about one-dimensional, it is only x. Now, the zero-dimensional space is where the vector has no magnitude and no direction. That's a strange world, but that's also there. The one-dimensional is also confusing somewhat because it is often confused with just x. Now, x is by itself a scalar, and a scalar is just a magnitude. It doesn't have the concept of dimensions. Now, this is an important point. As I said, a vector is a displacement in dimensions, right? Now, what is a dimension then? A dimension is, in nature, a degree of freedom, a sort of an independent way in which nature can move or vary. Now, a scalar doesn't move or vary. A little bit of history here is that Hamilton, William Hamilton, who was Irish, he actually, in his paper on quaternions, reintroduced this word scalar. Before him it was Vieta, a French mathematician, but Hamilton officially put this word scalar to mean what we understand today. And it's from the Latin word scala, which means a ladder or a scale. And so you can climb up and down a magnitude scale. And he used the word vector from the Latin vihere, which is to carry in Latin. And so a vector encodes several things, but that encoding is you're traveling through a dimensional space. So x is a scalar, and that's important to understand because we are not talking about any direction here, but when we're talking about this, we're talking about a particular direction. So if you draw the xy coordinate, and if you say 5, then it is, let's say this is 5, then this is a vector. But if you represent the same point as a scalar, then it is just a dot, which is 5. It's a magnitude on this line. Has nothing to do with direction. And it could be magnitude here as well. It can be a magnitude here. So essentially, it can be a point anywhere with respect to any starting point. If the starting point is here, this 5 can represent a distance from this point to that point. Now, so that's why a scalar essentially has nothing to do with the directionality. It is just a dimensionless quantity, whereas a vector has something to do with dimensions, and those dimensions can be 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional, or in the general case, it can be n-dimensional. Now, when we talk about a list of something, for example, in data science or machine language. We don't often talk about this fact that these are along axis. So for example, when you talk about a picture, we talk about a picture being pixel 1 to, let's say, pixel 5 million. Now, this pixel 1 to pixel 5 million is a value between, let's say, 0 to 255. Now, this list of pixel values is actually lying in n-dimensional space of 5 million. So that's why that's why data science problems are high-dimensional problems, because the way we represent them. And sometimes we'll talk about the curse of dimensionality, etc. But it's important to understand that our X-ray images, our speech, everything essentially is eventually converted into a very high-dimensional vector, and that is how machine learning, etc., understands it. So that's vectors. Now let's look at something called the row picture and the column picture. So a row and column picture, and now we are trying to understand the geometric intuition behind the simultaneous equations that we have understood before, from the from the point of view of linear algebra. Now, let's say we have two equations, 2x minus y equals 0 and minus x plus 2y equals 3. Now, this is the example of a simultaneous equation because it is two linear equations, because you see here both x and y are raised to the power 1 and everything else is essentially a number or constant, right? So we talk about this one here. This is a constraint, and here each equation in this row picture, in our when we were kids, we only looked at the row picture. So this is the row picture that we're looking at, and each equation is essentially a line, and we will draw that line. And because we are in 2D, it is a line. If it is 3D, it is a plane. After 3D, we cannot visualize it anymore, but then it is called a hyperplane, and so on. But each equation is that. So if I want to draw it, here it's simple to draw because 2x minus y equals 0, so y equals to 2x. So if I take x equals to 1, then y is 2, so that is 1 point. And if I take x equals to 1, 2, 3, and of course 0 is also a point. If x is 0, y is 0, so I can just draw, because in straight lines, in case of lines, you just need 2 points. So 1 point is 0, 0, and another point is to 1. So this is the line here. The other line, minus x, so if we put minus 1 and if we put 2, so that this point is there. If we put x equals 0, then y is 3.5, so 1, 2, 3.5. So this is another point, so it passes through this, right? Now this is the intersecting point. When we were kids, we used a bracket and we used to write 1, 2, but we won't write that here anymore because we are in the vector world. So we will write it as 1, 2. 1 being the x is equal to 1 and 2y. So this is the intersection point. So what does the intersection point mean? It means that this first line and this second line has something common that it agrees on in the input space. So when we were talking about the row picture, we're talking about input space, which is x and y. When we talk about the column picture, this guy, we are talking about the output space. What is the output space? Now we understand, we have to convert this into a matrix notation. So what is the matrix notation? The matrix notation is we just take the coefficients 2, minus 1, minus 1, 2, and this is our variable vector, and this is so this is written generally in the form of a x. This x is capital, and this is b. This is the vector. So this b, which is essentially b1, b2, is the output axis. So if we draw this, this is b1, this is b2. So what is this telling us? It is telling us, if I use that example, this the result from this first the row picture, which is 1, 2, it is telling me if I take 1 of 2 minus 1 and take 2 of minus 1, 2, I should land up at 0, 3. Do I do that? Yes, I do that, because if I add 2 minus 4 and minus 1 and minus 1 plus 4, x equals 1 and y equals, so I have 1, 2 minus 1 plus 2 minus 2, so I have 1, 2 minus 2 and minus 1 plus 4, so that actually gives me 0, 3. Now, can I see that in the diagram? Of course I can. So this is my first column vector. This is the coefficients of x, right? So I go 2 points in this direction and 1 point in this direction. This is one vector. This is my 2 minus 1 vector. And minus 1 is in this direction and 2 is in this direction. This is the other vector. So this is our minus 1, 2 vector. So what this is saying is that if I take 1 of this and 2 of this other one, I end up at a point which is 0, 3. And indeed that is the 0, 3 point. So the column picture is how much of the column vector ingredients do I use to get to the output space, which is what we found out here. Now, this matrix A in linear algebra is not just converting one point into another point, as it seems to be the case here, because we can take many points in this space. Any point in this space we can take, and we can use that. And the question that it's asking in the case of column space is, can we reach it? In the case of the row space, we are actually asking a different question, but it's about the constraint. The column space is the output space, and so here we are talking about the reachability, but the matrix acts like a machine, and that is what in linear algebra we understand the matrix to be as. So this A, for example, if you talk about a simple equation like in life, 5x is equal to 10, right? So what is this 5 doing? It is basically working on this x and making it 10, right? And from this we can find out what this x is. In this case, this is elementary algebra, so we get 2. In ax equals b, it is something similar. This A, matrix A, is a linear transformation. It's a modifier, and this modifier asking questions like, does it stretch it, does it flatten it, does it rotate it, does it crush it, or crush some directions to 0, does it preserve some directions, does it mix variables, does it lose information, does it amplify noise, or does it reveal some hidden structure? So all this is possible because of we are converting simultaneous a system of simultaneous equation into this matrix form, and this matrix is that machine of linear transformation. Now I want to cover one more thing in this input space, this first example. This is our row vector. So like this was the column 1, this was the column 2. Similarly, this one is row 1 and this one is row 2. Now this row 1, 2 minus 1, is actually not representing this line. It is actually representing a vector that is perpendicular to this line. So 2 minus 1 is representing a vector that is perpendicular to this line, and we can see that very easily for let's say any general line in the form of ax plus by equals c. If I put let's say I have 2 points, x1 y1 and x2 y2. If I put the first point, I have ax1 plus by1 is equal to c. If I put the second one, ax2 plus by2 is equal to c. If I subtract, what I get is a x1 minus x2 plus b y1 minus y2 is equal to 0. Now you see, this is actually the same as writing the vector AV and the vector x1 minus x2 and y1 minus y2 dot product. So what it's saying is that this is perpendicular to the line, to the direction of the line, right? So you can actually easily see that if you also use one particular, instead of a general case. If I take this line, for example, the x1 and x2, let's say one example of x1 and x2 is in this case 0 and 0. The other example is, let's say y is equal to 2x. So if x is 1, y is equal to 2. So if this is point P and this is point Q, the direction vector is Q minus P. So that is basically 1 minus 0, 2 minus 0, that is 1, 2. Now if I take the row vector, which is this, so if I take 2 minus 1 and do a dot product with 1, 2, what do I get? 2 minus 2 equals 0. So this line is perpendicular to the vector represented by 2 minus 1. Now let me take a medical example. Now I'm sort of making this up, but it's not too far from reality. So what I'm claiming in this story example is that age and systolic blood pressure is a factor in two kinds of complications with the heart. One is cardiovascular disease, and the other is the incidence of stroke. So let me write those equations down. So now, before I do that, now it's important to understand that because we have this, first we are talking about the row picture, right? We have x and we have y. There's obviously a 0. Now in this case, I am contriving, that is, I am essentially talking about a deviation. So my origin is that is age 0 is not 0, it's actually 60 years. That's practical because heart diseases, most of the complications happen with the elderly. Then we have the systolic blood pressure, and that is, let's say, 130 millimeter of mercury. Now, so this x that we are talking about is the real age minus 60, and this y is equal to the systolic blood pressure minus 130. So we will make those adjustments when we do this experiment, when we do this example of this particular case, and I assume that all other vascular risk factors are constant for the story example. So the equation that we have is 0.4x plus 0.06y equals 1.40, and 0.3x plus 0.1y equals 1.60. Right? So what is this first equation telling us? This first equation is telling us how all age and systolic blood pressure combinations above a particular point, which is 60 years and 130 millimeter Hg, increases the cardiovascular disease risk. That is the first. So this is about CVD risk. And the second equation is telling me how all age and SBP combination increases the stroke risk. So this is about stroke risk. Right? Those are the two equations. Now, if I solve it, I find that I've already done this. So if I solve it, I find that this particular point is 210. And what it means is that if it is 210, then the actual age is 62. So for the solution to this is the age is 62 and the SBP is 140, right? That is the particular case where both of these things will happen. If you are at the age of 62 and if your SBP is 140, you will have an elevated CVD risk of 1.4 and stroke risk of 1.6, and that is what this equation tells you. Now, if you look at the output, so this was the input space, right? So what is the input space about? So the input space essentially is, this is our input space, is essentially delta age, right? And this is essentially delta SBP. So what are these? These are predictors, right? What is our output space? Well, the output space is these values, right? So if I write this as a metric expression, I have 0.4, 0.3, 0.06, 0.1, and I have x and I have y, and this is my B1, B2, and B1 is 1.4 and B2 is 1.6. So this is my output space, right? So this B1 that we are talking about here is the change in cardiovascular risk index, right? So I can write this as del risk of CVD. And similarly, I can write this to be del risk of stroke, right? That is the stroke index. So again, we can plot it with 2 and 10. So in this case, this is the column vector. This is the age factor column vector, and this is the systolic blood pressure column vector. And if we multiply 2 times the age factor column vector plus 10 times the systolic blood pressure column vector, then we arrive at 1.40 and 1.60. That is the diagram that we would get here. I'm not drawing the diagram, but just explain what it is. So essentially it is 2 times 0.4, 0.3 plus 10, 0.06, 0.1 is equal to this 1.4, 1.6. This is the column picture. So that ends the example that I wanted to talk about. Now I will just talk about what are some of the things that this course will cover. So now this course will, as I said, I'll go through a lot of essentials about linear algebra that will help us understand healthcare IT from the artificial intelligence perspective. So there will be language and notation, there will be geometric intuition, there will be basic vector operations, system of equations, solving system of equations like what we saw here. There will be matrix operations, there will be vector spaces and structures. We will talk about linear transformations, we'll talk about determinants, and essentially determinants are areas and volumes. We will talk about orthogonality and approximation. We'll talk about eigenvalues, and so essentially eigentheory. We'll talk about special matrices, including spectrals. We'll talk about matrix factorizations, which is something that we'll talk about in the next class, starting with A equals LU. And we will talk about numerical linear algebra, abstract and advanced linear algebra, parts of it that are essential for understanding machine learning, optimization, and statistics. Essentially, statistics, when looked at from the perspective of vectors, has a very geometric intuition. We'll look at that. And we'll look at all of this through the lens of machine learning and AI from the perspective of healthcare and healthcare IT, as I did here in this first more detailed class. And there will be some other scientific and engineering examples, some essentially from computer graphics and robotics that are essential to understand this at depth, networks and discrete systems, but most of the stress will be on the tools and computations, some of the mathematical tools and computations like what we understood today, and through the healthcare and biological applications. So that is essentially the summary, and this ends this second video, and in the next video we'll talk about matrix factorizations.